Okay, so welcome everyone to our STAMPS webinar series. It's a pleasure to introduce Dr. Viviana Acquaviva. And Dr. Acquaviva is a professor of physics in the City University of New York. And she received her PhD in astrophysics from the International School for Advanced Studies in Trieste. Viviana has an impressive and pretty fascinating career path. So after establishing herself as a very successful astrophysicist, and I just saw that um, she's also been listed by Wired as one of 50 women who are doing the history of computer science. It's a real accomplishment. And also one of Italy's 50 most influential women in tech. And she's done quite a lot of work in physics. And before she started a second career in climate data science, funded by a Pivot Fellowship and the Pivot Research Award by the Simons Foundation. And her current research is on developing new metrics to assess the performance of global climate models and on reconstructing full spatial temporal fields, in particular ocean carbon, from limited and biased data. She's also working with early career scientists on how generative AI tools can be responsibly incorporated into the scientific workflow. She has recently written a textbook, Machine Learning for Physics and Astronomy, which won the 2024 Chambliss Astronomical Writing Award from the American Astronomical Society. And today, Viviana will talk about learning from simulations using statistics, machine learning, and AI. So Viviana, please take it from here.
Thank you so much, Anne, for the invitation and for such a kind and flattering introduction. It's a pleasure for me to be here and to be able to connect with you all, at least online. And just, sorry, maybe I should have asked earlier, but do you tend to go to the hours? Do you prefer maybe me to keep it to like 45, 50 minute-ish? So, okay, perfect. Okay, so I have like a watch next to me. And I'll do my best, but feel free, if you see like that things are going a little bit long, feel free to rein me in. Okay, so I think has been mentioned, I am a former astrophysicist. And so I think something that has been common to my entire career is the fact that I tend to get bored quite easily. I tend to like broad more than deep. And so even when I was working in astrophysics, I sort of like jump around like different set of topics. I started in my master's thesis. I was doing pen and paper things about non-Gaussianity from inflation. I guess nowadays they wouldn't be pen and paper, but back then there weren't packages to do this. And then I work on different aspects of cosmology. In my second postdocs, I started working on spectral energy distribution fitting of galaxies, and this is sort of like a theme that has continued, just basically how we can understand the properties of galaxies in galaxy evolution in simulations. But in a sense, the common theme for my entire career in astrophysics that has actually persisted through my pivot has been a real passion for like statistical tools, and then early on machine learning. I started sort of studying and practices in the early 2010s, where this was actually not as popular as it is today. So again, I want to talk about my pivot because this is actually an ongoing program. And I think, I feel like one of the things that I really enjoy doing is to help or chat with at least people who are considering a similar career shift. I think that there should be many more, but as we know in academia, we are often encouraged to keep working on the same thing over and over. And so I feel like when there are programs that actually encourage you to do something a bit different, I think it's good to advertise them. So I was in the first ever class of Pivot Fellows, but basically the foundation, Simons Foundation, has been funding about 7 or 8 of these yearly. What I love is that you received a year of training and you have to choose a mentor. I actually had two, Gillian McKinley, who I'll talk more about later, and Pierre Gentine. And they also commit to helping you succeed. And of course, I think that, in 1 year, you're not going to learn a new field, but I think it's reasonable to establish connections and collaboration, figuring out what you want to work on. And then something that is also, I think, really cool is that afterwards you get the chance to apply for this larger, like it's 1.5 millions before indirect costs, Pivot Research Award, which is, supposed to help you build a group in the new field. So again, if, anybody in the audience is curious about this program, I'm always happy to share my experience and my materials. So I did that in 2023. And this is a slide that comes from my pivot application. I've thought about this a lot because, I was thinking, okay, I've been working in this field of galaxy evolution, galaxy formation, simulations for a long time. And when I didn't know anything about climate when I started, well, I knew that I was interested. And the reason why I knew I was interested is that when I was doing research for my book, I spent a lot of time reading paper outside astronomy because I wanted to figure out, some application of machine learning outside my stomping grounds. And I noticed that I found this like geophysics, climate papers extremely interesting. But then I realized that there are a lot of common themes, right? These are both fields that heavily rely on simulations. They are multi-scale and extremely interactive. In fact, I thought that this was an issue in astronomy, but I have to say that this is much more of an issue in climate science. I found climate to be much more dynamic than astrophysics is. I think in astro we can often get away with saying, okay, we study galaxies, so we don't care about stars. But for me, one of my most shocking revelations at the very beginning was to learn that the biggest uncertainty in global climate models, when we need to predict temperatures, like, far away from now, and temperature is like, sort of like a global variable, well, the biggest uncertainty comes from the modeling of clouds. So this is sort of like a level of coupling of different scales and physical phenomena that I hadn't seen before. And so in both cases, you have the need for mixing and matching resolutions. Sometimes you don't have enough computational power to resolve small scale processes. And so you need to understand how to derive parameterization or physical models that can, give you at least an effective description of the phenomena you're interested in. So I found that, at least in terms of methods, I felt like I could establish time continuity. So one of my challenges, and something that I love sharing, I feel like this has been in every single talk I've given in the past couple of years, is this diagram. I feel like one challenging, in a good way, issue that I had was that, when you're given the chance to pivot, then now you have sort of like blank slate. I think in my, let's say, PhD, I basically figured out, okay, I'm interested in cosmology and I love this advisor, this is it. Here I felt like that, I had a lot more choices. And so I spent a lot of time with this diagram trying to figure out what lives at the intersection of something that is useful to do in the field, something that I am at least reasonably good at, or I can become good at, and something that brings me joy. And I feel like this is something that we don't emphasize enough, but I feel like this is really what makes the difference between being miserable and being happy in going to work every day. So I think it's actually super important. And these are the things that I came up with, something that, Anne has mentioned already. One is looking at assessing how well global climate models are predicting future weather and climate. One is looking at the ocean carbon cycle, but from my personal perspective of a data person, someone who enjoys thinking about, how we can use the information that we have in useful ways. And I've also been thinking a lot about how AI tools can be used for ethics, for explainability, and more recently, just to accelerate or simplify our workflow. So I'll try to touch upon each of these themes. And this is a slide that I feel, is my attempt at finding some sort of unifying thread in my work across the years. And I call it learning from simulations. So these bubbles are different things that I'm generally interested in. Multi-scale tools, representation learning, improved inference, physical models, and uncertainty quantification. And in red are things that I am actively working on or I have worked on. But in general, these are all things that I find fascinating and I wish I knew more about. So let's give some examples. I feel like I want to go back to my astrophysics background for a bit, just to tell you, a bit about my process over the past decade. So we're going quite a bit back to circa 2017. The problem that I was dealing with at that time is the one of, wanting to learn something about galaxies and the physical properties of galaxies. And of course, the challenge that we have is that when we look at galaxies, even when we can take like really pretty pictures, we get some emission chart that tells us how bright the galaxy is at different wavelengths. But we need an inference process to go to the physical properties. And for a very long time, the name of this game was spectral energy distribution fitting. It's just a process of saying, okay, if I have a model, and for a model galaxies, the physical properties are known, I can now sort of like forward model this and turn into a spectra, and then combine this spectrum with what I observe, and then, sort of refine this procedure until the spectrum or the images of the model galaxy and the one of the data are close. And at that time, we had the idea of saying, hey, you know what? Can we do something different? And to take the road less traveled, that, believe it or not, at that time was machine learning. So here's what we did together with Chris Lovell, who at the moment is like a senior research scientist in Cambridge. At that time, he was a graduate student who came to visit me for 6 months to work on this crazy project. And so our idea was, okay, we know that we now have cosmological simulations that are reasonably good. And cosmological simulations are things that can model the way the galaxies form from these sort of like, clouds of dark and luminous matters. So we had two called Illustris and Eagle. And we figure, okay, we can use these simulations to generate realistic spectra of galaxies and then teach some machine learning algorithm. At that time, we use a convolutional neural network. What's the connections between the star formation history, how the galaxy has been assembling its stars, like something that you can see here in these curves. In some cases, like galaxies have a lot of gas, so they form a lot of stars, and then they run out of gas, and then sort of like their star formation decreases. But, this can happen in many different ways according to whether the galaxy is interacting with its neighbors, whether it lives in isolation, and so on. So we did that, and we did have, I would say, pretty decent results. I've chosen not to really discuss them here, just in the interest of time. But one thing I want to mention is that a problem that we always have in simulations is how do we check, right, that our results hold in a more general setting, right? If we're learning something on simulations, how do we make sure that we're learning something about the physics of galaxies in this case, rather than the specific nooks and crannies of that one simulation? So this is hard to do, of course, on real data where we don't have any ground truth. But what we could do at that time was to check how our chosen metric, which was the symmetric median average percentage error, or SMAPE, would fare when we apply, when we do sort of training and testing within the same simulations, which is this like dotted line here, and across simulations. And, without really going into details, I think what we could say is that this MAPE didn't blow up when the model is trained on one simulations and then apply to the other. So that warranted a little victory dance. But I feel like for me, what I was left with when we finally published this paper in 2019 was this burning question that I think would really affect the next decade of my work, which is there are so many cases where we can only train model on simulations, right? And then we need to apply them to data. Right? And rule number one of machine learning is that if you haven't trained your model in the same conditions, you cannot trust what it will do. So my question was, what would it take to trust machine learning models that are trained on simulations to also work in the real world? So the way I thought about this is that if we knew that simulations and data are identical, right? From every perspective, every detail that you can measure, every possible observation and angle, then I think we will feel pretty confident that training on one means that we can apply to the other domain. Now, of course, this is never the case, but in many cases, data and simulation are actually reasonably similar. Right? And so I think we could say that we probably want to say that even if we train on simulations, our model would retain a certain degree of reliability also on observations. So how can we quantify this a little bit better? We have these funny shapes that I made and sorry about them. I don't know, I feel like at this point I have grown affection to them. But basically what I was trying to do here is, can we somehow formalize this notion of similarity as a function of the distance between the training domain and the application domain? So in this case, I'm defining some setup, let's say, right, where the observed space. Okay. Oh, the observed space is this like sort of like weird red shapes, but just to be clear, these are still spectra of galaxies in both cases. And so we have our training domain is the one of simulations, and our application domain is the one of observations. And these, the spectra, are the things that we can observe. Then we have the space of inference. The space of inference will leave the physical properties of the galaxies, for example, the stellar mass, the star formation histories, and this is, of course, the same here for simulation. Sorry, I went back instead of forward. Now, in the space of observations, we can potentially measure similarity. So how do we do the inference? Well, in nature, there is an actual true function that here I called f that basically says, okay, if a galaxy has these physical properties, then its spectrum will look like that. This is what we would really like to learn, right? The sort of like holy grail of how nature works. Of course, in the domain of simulations, there is also a correspondence between the physical property of a galaxy and how its spectrum looks like. And this is a function that we can know, right? We make this function. This is how we model galaxies, right? In an ideal place, F and G in an ideal world would be exactly the same. Now, what we really would like to learn is the inverse function of F, right? Basically, how do I go from the spectra that I observe to the physical properties of the galaxies, which is what I'm interested in. And we cannot learn this directly, right? But what we can do is to learn the inverse of G. So this is, so far, I haven't really said anything new. I've just defined some functions that I hope will be useful to show you what I was thinking about this formalization. So now let's think about how the inference process works. Let's say that I have some physical properties of galaxies in simulations. Because I know my modeling function G, I can create some simulated spectra. And then I can also learn through machine learning, for example, how to do the inverse process or, through other inference methods. And I will infer some physical properties for these galaxies. And most likely they're not going to be exactly the same of the true simulated physical properties of these galaxies. I will make an error. And in many cases, when I use machine learning, the error decomposes as these three terms: a noise, a bias square, and a variance. For us, this is actually not particularly important. Now, what happens if I now compare simulations with observed spectra? Let's say that there is a distance matrix between them. And here is my inference process in the space of the real world. So a galaxy has some true physical properties. They are connected to the observed spectra by the unknown function f. As we said, we cannot learn the inverse of f directly. The best that we can do is to apply the inverse function g, the one that takes me from simulated spectra to infer physical properties, also to the observations. And I will infer some physical properties also for the real galaxies. And of course, I will make an error here, which is a distance in this axis. And my hypothesis is, can I find an appropriate distance metric d so that the additional error that I make is proportional to this distance? And why does it matter? Well, because if there is such a thing, then the distance, which is something that I can measure, the distance between observation and simulations, is a proxy for the additional error that my machine learning models trained on simulation will make when I apply them to observations. And just to be clear, I didn't really have any sort of formal sense of whether this would be true. I was just looking for some sort of empirical recipe for this. So I spent a lot of time thinking about distances between distributions. I started thinking that this could be one of the classic measure of distances between distributions, but then I abandoned this idea because I figured that this distance metric can't be agnostic to the problem we're trying to solve. And the examples I had for this is that, let's say that we have models that try to determine stellar mass. Then in a spectrum, stellar mass is determined by the rest from near infrared of the galaxy. And so what matters is whether models, simulations, are a faithful representation of reality in that specific region. If we were to measure that, we would be looking at different regions where we know there is more information. So we created, very simply, we just did some feature importances on the different features of spectra. And we said, okay, we are just going to look at distance, but restricted to the space of the features that are most important. And we started testing this idea using stellar mass, which is the easiest problem in SED fitting. And by the way, I don't really see the Zoom commands, but feel free to interrupt me if you have questions. I'm not, I'm happy to answer even during the talk. So how could we test this idea? Of course, on data, there is no way we can know the real, stellar mass of galaxies. So we had to use simulations for this. And we generated 20 sets of simulations, hoping to represent sort of the spread of models. And then we calculated distances between data sets. And then we trained 20 models, one per set of simulations, so that we have basically 20 inverse modeling functions, g to the -1. And then we calculated the generalization error obtained when we apply these 20 functions to each simulation set. So to the one where the model was trained, as well as the other 19. And we populated 20 of these plots. This is the distance matrix between data sets. Let's say that I'm using the inverse function that I learned on dataset 1. This will have the distance between dataset 1 and the other 20. And then here, the mean square error in the input parameters and infer parameters. Again, looking at each dataset and the other 19. And what I'm asking here, my hypothesis is, do I get a reasonably tight regression relationship? And the answer, like in many non-scientific application, is eh. So I think this is just one of the plots. I didn't choose the simulations one, but it's not particularly better or worse than the others. You can see that there is a correlation. You can also see that there are some strange points. This is really where there were like different modeling issues in like binary stars, for example. So this was like encouraging enough to keep us going, but also perhaps not tight enough to say, okay, we have solved this problem. So we had planned to continue this investigation. In fact, we did for a bit. And again, the reason why I wanted this to work is because now when I have, let's say that data, like real galaxies, live somewhere on this x-axis, right? At a distance from simulations that I can somehow measure, then I can just sort of like go up on this, let's say, linear relationship and look up what's the expected mean square error for observations along that method. So the plan was to generalize this framework to other quantities and metrics. Instead, we actually spent a few years thinking about whether spectra are the best representation of galaxies. Of course, the answer is no. But I would say that the segue here for me is that even when I transitioned to climate science, I spent a lot of time thinking about similarities and improved representations. And because the structures that we use in climate, so for example, here in this slide also comes from my pivot fellowship proposal. Here on the left, you have like 9 simulations of the Earth system. I'm just gonna tell you that the real Earth is the one in the middle. On the other side, you have simulated galaxies. There is no Milky Way there. I think, hopefully this is obvious why that's the case. But the idea is like when you have this complex data structure, right? You're moving from catalogs or spectra to maps or time series. How do we even define similarity, right? What do you measure if you want to say that your models are correct or reasonable? So this is the first project that I formulated, let's say, in climate. And the idea was that, when we look at outputs of climate models, we often use maps as our main data structure. So these are like 4 different Earth system models, like global Earth system model. CHESM, for example, is the community Earth system model, and IPSL, GFDL, and MIRAC. These are like 3 different data labs. Then those are just like differences in the prediction of precipitation for a random month, I think January of 2050. Now, not particularly important, but you see here that there are the structures in these maps. And if I ask you, okay, which models are closest? This is like, the difference, like this one model with the other 3. This is not a trivial question. Like, yes, you can see that there are similarities, there are differences, there are some red and blue points. So a lot of times, metrics that are used are sort of pixel-wise point-like metrics. For example, the root mean square error calculated pixel by pixel. But these have many limitations. And in particular, I think that when we look at these maps, we don't want to penalize, like, I don't know, let's say a precipitation system that is slightly shifted exactly in the same way that we would do if that precipitation system is in a completely different place, right? You want to be sensitive to where you are in the map, in whether the structures look similar, in whether, of course, like the magnitude of the structures look similar. So I put together a proposal and hired this very talented postdoc, Gabriela Carino, who's at Columbia and working with us. And I also enlisted some trusted and smart collaborators who could, definitely help guide me in this new field. We call this project the Metrics Reloaded. And we started basically by looking at the literature and trying to figure out, okay, what kind of things do we want? And, where, the world of image processing, computer vision can help us. So we wanted something that, in a way, matched perceptual similarity, but we also abandoned the idea that sort of like a human assessment could really be the ground truth in this case. So we just had the list of requirements. We want to be sensitive to large-scale bias, which means that, if two maps have different means, we need to give a pretty big penalty to this. We want to be sensitive to where spatial structures are. And ideally, we want it to be sensitive to multi-scale variability, because this is something, climate is a field in which you can sometimes associate a certain physical scale with physical phenomena. And so being able to say, okay, our maps get the large scale right, but the small scale incorrect, does tell you something about whether in your model you need to adjust the modeling of physical processes. So we like this structure similarity index measure that has this three component called brightness, contrast, and covariance. So brightness is magnitude, like contrast. Well, I guess they're pretty self-explanatory probably for this audience. And then we also took from this HAR perceptual similarity index the idea of wavelet-based decomposition, of using wavelet as a way of separating information at different scales. So to me, this is still, it's probably a simple but a very fascinating picture that I like to show the effect of wavelet decompositions. These here are two maps. You can see that the large scale structure is the same, but we did perturb the second one with sort of like this small scale noise. And these here are the wavelet coefficients. The bigger plots are for the finest scale, and the smaller plots are for coarser and coarser resolutions. And so because of that, they have fewer and fewer pixels. And so you can see here that if you look at the coefficient maps, the smallest map, which is the largest scale, is essentially the same in the two plots. And then the finest scales, which are like the large matrices here, these three here and these three here, they look pretty different. So I feel like it's a really effective way of splitting up information. And so we decided to use that as well. And so in the end, we ended up thinking about, maintaining from the structure similarity index, this idea of having three components. One is magnitude, is basically where the energy in the coefficients is located. One is displacement, which basically, when we look at the spatial distribution of wavelet coefficients, and if you think about this as a curve, we see how much, the center of mass of that curve is different. And then finally, a structural, which is, I think is the one that is a bit least intuitive mathematically, but basically is looking at the covariance of different structures and figuring out whether the patterns are preserved. So this is the metric that we created. We have a recent paper on arXiv that is currently under review. But the idea is that we have a metric that is a sum across different scales. So it's just a decomposition. And then here we have a product of the contribution of these three different components: magnitude, displacement, and structure. At the moment, they are sort of accounted in the same way. but one can use these coefficients, alpha, beta, and gamma, to control the trade-off between the three components. And then, of course, you can also have a weighting scheme, and the weights will privilege one scale over the other. And one of the reasons why we did that is that, as I mentioned, we sort of abandoned the idea of having one summary statistic that is better than others. And we just figured that what we wanted to do instead was to open up this axis of analysis so that people can use this in different ways. I'll show you, for example, this on a synthetic. We did actually a pretty detailed study on synthetic test cases. And so here we have, this is like a map of precipitation from some reanalysis model called ERA5. And this is like a tiny shift. This is a bigger shift. And this is a horizontal flip. So this is how our metric behaves. Okay, but just like the normalized root mean square error or the structure similarity index, you can see that the metric, like the measure similarity, decreases monotonically for all three. The things that I really like about WaveSim is that it's able to tell you how the similarity behaves at different physical scales and to split it up in these three components. So for example, while all three of this measure tells us that this last map is pretty different from the first one, I think in WaveSim, we can see that all the difference comes from the displacement of structures, right? But the magnitude and the structure component are the same. And we also try this on Earth system models. Is the case in which, again, we have what we call data, which is, it's really a mix of data and model. It's model after data simulation. And here are three different models. These are sort of like big maps of sort of average pressure. Actually, it's altitude at a certain pressure. And you can see that this, all the structures if you compare the first column with the second, for all the models, the structures are reasonably collocated. So the displacement component remains high at all scales, but we can attribute differences to magnitude or structure and also as a functional scale, which I think is interesting. So we are now looking at a few applications for this framework. One is to use it as a multi-scale loss function for emulators. So most of the emulators that we use for climate models are trained on an RMSC loss. But we're thinking that perhaps we can use WaveSim as a loss function. And in fact, now Gabriel is going a little farther than this and doing the denoising, or sort of like using a diffusion, like actually a flow matching scheme for this, and trying to do the representation learning and the embedding directly in wavelet space. So this is one possibility. Can we use a metric like WaveSim as something that is minimized when we build models of climate? The other things that we're doing, and I apologize because this slide is not pretty at all, but I can't figure out how to make it nicer, is that something that is very well known especially in AI-driven weather and climate models, is that they tend to collapse in performance, meaning having very similar root mean square error metrics across different variables and times. And so something that we are now trying to do with a grad student, David Adorno, who's coming to visit, is to sort of like open up these numbers and say, okay, maybe these two models have the same root mean square error when I look at, I don't know, precipitation at 5 days in ahead. But can I figure out, using the axis of WaveSim, this displacement, structure, and magnitude, whether I can be more specific about where the differences are coming from? And so this is our idea. At this point, I feel like, unfortunately, I can't really make a smoother transition, but I do want to talk to you also about my other sort of like big project, which is the one that is actually the topic of my Pivot Research Award. And this is a collaboration with several members of the McKinley research group at Columbia, including some that I haven't pictured here because I included the ones that are participating in the project that I will talk about. And so some of them come from my new world, and Romina Wild and Alessandro Laio, they're actually in Trieste. I'm also part of the theoretical and scientific data science group there. And so the idea here is how can we use some of these techniques to improve the reconstructions of sparse data? And I'm also hiring a few people through this project, so hopefully we'll also have more hands on deck. So I'll tell you a bit about the problem and why we care. So what we want to do is to reconstruct the field of surface ocean carbon in space and time. And the reason why we need to do this is because we have observations of ocean carbon, and they are sparse. As you can see, these are actually not all the years that we have, but I think it's like, maybe 2019 to 2021. You can see that the Northern Hemisphere is much better sampled, and the Southern Hemisphere has very little. This is just because there is a lot more land in the Northern Hemisphere, many more research cruises can travel. And then if I were to show you this in time, you also see that there is a strong bias in summer versus winter, just because winter in either hemisphere has a lot more ice. So we need a way of going from this picture to this picture. And the reason why this is important is that these so-called FCO2 products are a big part of what is used to estimate the ocean carbon sink in the global carbon budget. And the uncertainties that we have at the moment, this is actually, I haven't upgraded to 2025 yet, but it does look pretty similar. We still have pretty large uncertainties, not so much in the mean, which is known maybe to 20% precision, but on the trend, the seasonality, and so on. And the trend is something that is very important in the context of climate change. So smaller uncertainties there is something that can actually affect our plans for how we mitigate or adapt to climate change. So this is sort of like one big picture about how this process works. We cannot reconstruct the field directly because the data are too sparse for that. Even on a relatively coarse grid, let's say 1 degree by 1 degree at monthly resolution, you're only able to fill about 2% of grid cells. So it's sort of like hopeless to do this with some interpolation method. So what we do instead is we look at features that are a bit easier to measure from satellite, like temperature, salinity. We train machine learning models in going from the PCO2 measuring observations to these physical features. And then we use machine learning model to fill the gaps, the prediction from machine learning models to fill the gaps. And you can see the problem here is that we are applying our machine learning models to a domain that is very different. So there's a lot of things that we've been thinking about to improve both like the performance and sort of the reliability of this process. One thing that I'll briefly talk about is improved representation. And I guess I don't know how well you guys can interact with me, but I still ask the question.
Yeah, I'm monitoring the questions, so don't worry. You have about 10 minutes left.
Okay, super, perfect. Yeah. So representation is an important ingredient, right, in every machine learning setup. So let's say that, I give you this sort of 5 examples, and then I ask you to predict the output. Is anybody who's willing to try what would be the prediction for the number 6 if, given the ones for the other numbers that you know?
suppose I would predict 6.
Okay, that's a good guess. Okay, I'm gonna do one more thing and change my representation and ask if you're still happy with 6 or if somebody wants to propose something different.
It's going with 3.
And why 3?
A number of like letters in the word.
Yes, correct. Nice. I feel like, this is sort of like a simple example that I always like to use to say, you may have the same information, right? But if you are actually able to portray it in a relevant way, in a useful way, the learning process becomes easier. So for us, basically, we're looking for the equivalent for ocean features. And we have some requirements for that. Something that I think has been a difference between what I used to do in Astro and my climate work is that in climate, usually you want to be able to talk to very different communities. And so, for example, while doing, finding optimal representation through some embeddings is relatively easy, in many cases, if you want to talk to someone who is on a research ship, you cannot really say, okay, you should go and measure something embedding, right? You need to talk in terms of physical variables, of latitude and longitude and time of the year. And so the idea is like, what can we use to find representations that are physicals, but also problem aware and small for visualization? And this hinges on the idea of finding informative metrics. And so idea here is very simple. Let's say that we have just 2 variables or metrics and data that are distributed like this. Then you can see that if 2 points are close in X, they may be far away in Y, but the opposite actually doesn't hold. If 2 points are close in Y, you can also predict that they will be close in X. And so the interpretation of this is that Y is a more informative metric than X because the vicinity in Y is predictive of vicinity in X, but the other way around doesn't hold. So from this, you can have an idea, you can define distances in 2 metric spaces as neighbor ranks. So for example, here, J is the first neighbor of I in this space, but it's the third neighbors of I in this other space. And eventually, you can put this together to define this notion of information imbalance that is basically a measure of the loss of information going from one metric space to the next. It's defined of the average rank in space B of all the first neighbors from space A, which means that if metric A is very predictive, this will be a small numbers because close neighbors in A will tend to be close neighbors in B. And if metric A is not predictive, this will be a number that becomes closer to 1. So you can actually put metrics that are equivalent or contain each other or are orthogonal on this diagram. And we have used that to find a representation that lies in this part of the diagram. We're basically going from input variables to target, which is PCO2, is as small as possible. So this comes with a process that I will not describe, but I want to give you a sense of what the results are. So here, for example, we were exploring subspaces of 11 features, and for each dimension, you can find the one that is a simple weighted combination of the original features. So you're not defining an embedding, you're really just sort of like stretching the space with different ways that has the smallest possible information imbalance with the original space. And so this defines an optimal metric, and you can do a lot of things with that. These are just a couple of my favorite one. One is basically power up simple models, even like k nearest neighbors becomes, in a space of 5 variable, it becomes more performant than actually the current leading method, which is XGBoost. One thing that we're exploring now, this is the first time that I show this plot, but don't read too much into it. But the idea is that you can actually compare how different variables, in our case, this is PCO2, are represented in different models and compare this to data. So this is, in a way, somewhat similar to what we do with feature importance, but this is algorithm independent. There is no machine learning here. This is just a representation of information in metric spaces. And same things, once you have like a few important variables that are correctly normalized, you can start doing things like symbolic regression to look for physical models. Now, I don't love the idea of, I don't know. I feel like I'm very hardly ever successful with symbolic regression, but I like this as an hypothesis for physical models. Okay, I think in the interest of time, maybe I will leave this part largely untold. This is just to say that I spend a lot of time thinking about the challenges posed by AI, especially when it comes to access. This slide comes already from August 2021, where we had noticed that only a small part of the community had access to ML tools, and now I feel like this has become more of a societal issue. So we looked at this in this workshop and paper where we sort of came up with some notes, perhaps. And this is sort of just my concluding thoughts. I'm thinking a lot about how our role of scientists is changing in view of AI. And I feel like a very common point of view, at least in my community, is that AI is here, whether we like it or not, so better adapt and become extinct. And my point of view is that I think it's super crucial to empower young scientists to make informed decisions. So for example, for me, this means that this semester I'm teaching a class called Large Language Models for Science. It's, the class in which I had the most to just give up the idea that I'm the person who knows and I am teaching as much as, I'm willing to be there and create a space where we can discuss this. But I would like to actually leave you with some questions, especially for early career researchers, because I think it would be important to think about which parts of our job we want to keep, to understand more about what is creative work and how we can protect it. And I'll stop here. Thank you.